Billet blocks. What makes them special? What are they? And how do you set them up? So everyone knows what a billet block is. They're in heaps of cars now. Super common, any high performance engine build, drag car, even street cars, circuit cars, all run billet blocks for different reasons. For the most reason though is to make sure they can support the power they're trying to make, with the cast iron factory block can't keep up. So the most obvious difference is it's billet. It's not a cast block. It's machined from a solid piece of billet, which makes it quite an expensive part to build. You can imagine it's a big piece of billet. A lot of material comes out. It's a big process to get this to the point where it sits now. This is a billet block out of Australia. They do a variety of different engines, and this is their RB version. So we're going to talk through this RB build from what goes into machining it, the components we use, and how we set up our cylinder heads to make this kind of grunt. Starting with the block and the components that support it, oiling system is super important on any performance race engine, especially on the RBs to keep them happy. A lot of these engines with these billet blocks will be running a dry sump setup. If you don't understand what a dry sump setup is, I suggest you go look that up. Have a good understanding of that if you're into race cars, performance cars, or you're looking at doing that yourself. This is a street application, this build. So this is going to be running a wet sump, a conventional wet sump, but it will be running an external oil pump. And the reason we're doing this is to get the most oil volume and most oil pressure we can to support this engine. When you have a conventional oil pump that's mounted to the front of an engine like a 2J or RB, or most engines that are run off the front of the crank snout, you're always limited to how much room and area you have to create the best flowing or volume pump that you can get. When you have an external oil pump like we're going to be running on this, that'll run on a belt on the front of the hammock balancer, you're not limited to rotor width or rotor size or rotor design. You can get the most out of the pump, and we can make sure this engine is super happy oiling wise. So the reason that is important, and the reason we want good oil flow and good oil support for this engine, billet blocks love to grow. They have a mind of their own. They do all these things that you can't predict, or you try to predict when you're building them. So the main thing we're trying to tackle is the growth. So what we're seeing cold is nothing like it's going to be when it's hot. So you really have to try and guess and or heat the block up and measure it to see how the thing's going to react. So a good friend of mine who builds engines and billet blocks, he had one of these blocks set up and they had it heated to full running temperature. And to give you an idea, the block grew 1.5 mil or 60 thou longer just getting it from cold to running temperature. So you can imagine what that means for liners being supported with the material around them, deck growth, all these things come into it when you're trying to build these things and get them as perfect as possible. So the first thing we try to tackle with block growth with a billet block is main bearing clearances. So the main bearing tunnel is going to grow so much when it goes from cold to hot, and you still want good main bearing clearance when it's hot. You don't want it too big. If the bearing clearance is too big, you're going to flow too much oil. You're going to, one, pump a whole lot of engine oil around the engine that you don't need to. Two, you're going to lose good oil pressure to your big end bearings because you're not going to have a tight seal around your main. That is just all things that are going to cause problems and potentially have a failure because you've got too much oil clearance or bearing clearance on the mains. So what we do is we start by cleaning this block up, torquing it, and quickly align honing the block. So these are a semi-finished machine surface. So the bores aren't to size. The main tunnel is true, but we like to flick it. We like to realign hone it to make sure it's 100% so we know exactly what's going together like. So that means torquing all the mains up, flicking the main tunnel with an align honing process, and then once we've done that, we use a 0.025 bearing, which is an undersized bearing. The reason we do that is because we're only looking for about 1.2 to 1.3 main bearing clearance cold, which is extremely tight. We've found it a lot easier to start with a 0.025 undersized bearing and then grind the main journals on the crank, normally around 1 to 1.5 thou to get them to where we want. If you want to go through and put a set of bearings in and try juggle bearings and try put half sets in, you'll always not be bang on where you want. So we've found it's much easier to go through that process and do it that way. The next thing we'll do, this is a street car, so it is still wet deck. So it still has the water system running as factory. That comes through the block and through the head. So it's running a conventional Nitto head gasket, which we've seen good success into 1500, 1550 wheel horsepower and RB setups. What we like to do is put a torque plate on the liners. This is for peace of mind for us. Torque the liners up or torque the torque plate up, put the block in the hot wash and get the block hot. This just means all the liners will settle in and they'll relax and go into the block and sit hard home. Not saying Bullet hasn't done that, but we want to know that those liners are hard home and not going to move when the block's heated up for the first time or running the car. And once the torque plate's on, we do the standard bore and hone, give it the required piston to bore clearance we like to give it. And then, being wet deck, we will deck the liners. The liners are now settled after we've heated the block up. Being a wet deck running conventional head gasket, we like to run the liners, and this is suggested by Bullet as well, around 2 thou above the deck surface to give you that extra bit of support on the head gasket clamping pressure onto the cylinder head, just so when the block heats up, again, billet block growing a lot, the liners are fully supported and pushing hard home when the aluminium's all growing around it. Another thing to consider is deck height growth. We briefly talked about it before with the liners moving around, but what this affects is cam belt tension. And why that's important, because if you set it at a standard cam belt tension, RB26s have like a kind of a mechanical, like a manual setting on them. They don't have a hydraulic tensioner. If you set it at a normal tension and the block grew, the cam belt tension would be, I'd say maybe potentially bad enough to snap the belt. I know belts are pretty strong, but these things grow so much. So what you have to do for first startup, we set them reasonably tight, not too tight, and then we set the cam belt tension when the engine's at full temperature. This just means we've got the maximum tension we can put on it, because when the block gets cold, it's going to be very loose, which could cause problems if you set it too loose when it's hot. So that's the process. Another process you've got to go through, setting the cam belt tension, making sure you're happy with it, which means when you have a billet block owner, they have to be very aware about what's going on. So you've got tight main bearing clearance, so you have to let the engine heat up. You've got a loose cam belt when it's cold, you have to let the engine heat up to get tension to the cam belt. You could either scuff your main bearings or run your main bearings if you give it a big rev up cold. You could pop or slip a belt, jump some teeth in the belt if it's really loose. So again, billet block issues, but as long as you're aware of it, you're fine. Components, we're running a 2.8 litre Nitto stroker kit. It's running their wide journal. So the wide journal is a wider and bigger diameter journal than stock RB26. The wide journal helps with having a wider bearing. A larger bearing is going to take more load and spread it over more area. It also has a bigger pin. It goes from a 48 to a 50mm pin, so it gives you more support and more strength in the crank. It's running the I-beam rod and the heavy duty HD CP piston. This is also running a 1/2 inch head stud, which means we will have to drill the head out to get it to fit. The head bolts or head studs will not go through the head factory as they are. That's one more process you've got to go through to make sure the head can actually fit onto the block. RB26 cylinder head do's and don'ts. So if we start with the porting of a cylinder head to make that much grunt, what we've found is you can't be too greedy on the exhaust port. You can't go and open the thing up, knife edge all the dividers, open up all the area, because they will crack. They do not like material being taken out. They're a thin casting. That will cause you problems. So exhaust port wise, you need to keep it super simple. They will flow enough, even just on a cleanup. They do not need to be taken out to make that much power. The exhaust bump, which everyone knows RB26s have, that can be removed. But if you're removing the exhaust bump, don't remove it too far, because it is thin behind it. So I would be on the lean side, get it so the port is just symmetrical. Don't overdo it, because it does get thin. Not on all of them, but I think it's the N2 from memory. We've had them blow through, in other words. The divider, don't open up the area around the divider. The reason is RB26s have a prone issue of cracking the divider when you make big grunt and big heat in the exhaust port. So if you leave it super simple through the divider, through the area, through the window, leave that all stock. The valve guide, the boss around the valve guide, you can do what you like with that. You can remove it, you can knife edge it up. If you've got the guides out, you can make it look all pretty and get some nice flow around the side of the divider. And then valve seat cut, that's probably a bit more technical, talking about throat areas, valve sizes and everything else. Same with the intake port. RB26s are quite nice, but they have a factory blended machine mark. So we drag that back into the runner. We open the runner up slightly, not massive amount, but enough to get more volume and more airflow through. and then we put a nice seat cut and cut all the seats to suit the Ferrera plus 1 mil valves that are going to go in this head. Chambers. So chamber on RB26, if you go over 30-40 pound of boost, we always remove the squish bands right out to the chambers. There's going to be a few people that disagree with that. I grew up in an NA world of tuning, so I know how important squish bands was. So it took me a lot of convincing over the years to say remove the squish bands. In a lower horsepower application, turbo setup's a bit smaller. You could probably get away with a higher boost, a higher compression ratio, say 9.5 to 1, 9 to 1, still on the 85, but you're going to have more power off boost, you're going to have more responsive turbo setup, and just a better combo for using that amount of power. And you'll still be well inside the efficiencies of the fuel, with the E85 fuel. Once you start pushing 35-40 pound of boost, there's a whole other side of it that is quite hard to understand. My tuners understand it better than me because they see it in front of them. I'm the guy that does the work and makes sure the chambers are all blended, and we went back and forth a few times and did all this. 8 to 1 compression, E85, 1500 horsepower, remove the squish bands completely right at the chambers, blend them out, you get a more efficient burn, you can put more timing into it. The EGTs come down when you do this. You pretty much at that point maxed out E85 fuel at around that 1550, 1600 horsepower in an RB. The next one to go into is talking about methanol and how much better that is and how that can make more power and run more cooler. But for this, being a street car, being maxed out to run on E85 fuel, that's what we're going to do. That's when it works really well, and we're really happy with that combo we've kind of developed over the years. So yeah, RB26 chambers, grind them out, your best friend. Component wise, Ferrera plus 1 mil valve, like I talked about. Shimless Calford buckets. These are DLC coated 6.4 mil shimless buckets. If you're building an RB to this power level, go shimless. Do not put shims in it. Especially if you're running sequential box, backfires, aggressive limiters, you will valve float and have pops and bangs that we're doing things inside the exhaust manifold and exhaust port that you can't predict. So perfect world, yep, you could run shims, everything's happy, but when you start doing all those things that I just talked about, you will valve float and you will have problems. So use a shimless bucket. We'll use a DLC bucket from Calford's, super strong bucket. These things can run, we've had them running in our dirt track series. They come apart like brand new. You can't see a touch of wear on the DLC. The heavy duty valve spring package, 125 pound on the seat. It's with a single spring of the single platform. It's like a drop-in application, so there's no mucking around with double springs, trying to get the fits, trying to get them to fit within the bucket, within the retainer and all this carry on. Super nice spring, heaps of spring rate. They've run them in circuit cars, drag cars. They run them up to 11,000 RPM in extreme GTR over in Australia in a circuit setup where they get hammered lap after lap after lap. So that just kind of tells you how good these are and how overkill it would be in a little street car that's going to do 1500 horsepower and a couple of power runs a few times a month. It's running the SF reduced base circle camshafts. Super good cam. We run it in all our GTRs, RBs that are kind of 1400 horsepower plus. We've always had great success and they go really well. If you ever wondered though why a reduced base circle cam exists in RB land, so RBs have a main oil gallery that feeds the bucket bores, and the journals as well. That gallery, Nissan put it in a really stupid place, and it restricts how much valve lift you can have without exposing the oil gallery. So once the bucket comes down the bore to a certain point, if you push the bucket too far down, it exposes the oil gallery. So what the trick is and what all manufacturers do, they offer a reduced base circle cam, which allows you to get more lift into the valve. So they reduce the base circle, which lifts the bucket up. It changes the starting point of the bucket, which allows you to put more lift into the cam, get a bigger camshaft profile, which allows for more power. Although you go to a reduced base circle cam, you still are limited to a point, but it is a really good, smart way that the guys do it to give you more lift and to allow you to put these big profiles in to support the big power that we're seeing out of these. That wraps up the Billet Build 101. We kept it reasonably brief. There's heaps of other processes that go into making a race engine and making them perfect and making them last and making good power reliably. But that just kind of gives you an idea of what goes into building an RB26 version of a Billet block and what processes we have to go through to make these things happy. Let us know what you guys thought of the video. We are super keen to do more content around the dark art of performance engine building. Check out our socials. We post regularly with tech tips and interesting facts.
Check out hughesracebook.com for all our line of performance engine building tools. We have engine building specific JDM tools from RB, JZ, and more lines coming out shortly. So subscribe for more.